So suppose we want to come up with parametric representations for a rectangular equation. The easiest thing to do, and we'll start with number 28, we'll do a couple of these, is to let x equal t. Okay, so if we do that, then y is going to be negative 8t plus 3. So that's one representation. But suppose we want to find another representation. We've got a couple of different options. Here's what I like to do. I'm going to let x be equal to t cubed. Okay. Now, the reason I could use t cubed is because this guy is going to have the same span as this guy. So if we think about x equals t, I'm going to get out positive numbers and I'm going to get out negative numbers. Well, t cubed is going to do the same thing. I'm going to get out positives and I'm going to get out negatives. So if I do that, then I'm going to get y equals negative 8t cubed plus 3. Now, both of these are going to model the exact same equation, and we could always check that in Desmos. So let's go to Desmos and let's look at that. So my original equation, there's my rectangular equation. And we came up with t and negative 8t plus 3. Okay, if I set this, let's just go negative 10 to 10. Just so I can get an idea. You can see how those live right on top of each other. So this guy definitely models this. That's where we let x be t, and then we substitute it in. But we could do the same thing with t cubed, right? That's what I said. So t cubed, and we had negative 8t cubed plus 3. And you can see how that's giving us the same thing also. I'll go from negative 10 to 10 here. So you can see how that green one lives on top of the blue one, which lives on top of the brown one. So they're all modeling the same thing. Now, why could I not use t squared? Well, think about what happens when you plug in values for t. If you used a t squared here, then you would only get out positive numbers. And that's going to be a problem because then I'm not going to have everything modeled. See how we're leaving out part of this because we're only getting positive numbers out for x, whereas originally we were getting positive and negative numbers out for x. So you have to be careful what you pick. There's an infinite number of options that you could choose for that. The easiest is to let x be equal to t, but something like this would work also. We actually could also do y as t if we wanted another option. So then x would be equal to, well, let's think about this for a minute. So if we let y be equal to t, then t is going to go in for this. So t is going to equal negative 8x plus 3. And if we wanted to solve that for x, which is what we would want to do, we're going to subtract 3, and then we're going to divide by negative 8. So that would be another set of parametric equations. And like I said, there's an infinite number of ways to do that. So take a minute, pause the video, try number 30, see if you can come up with 2. So number 30 is going to work the same way. I'm going to start by letting x equal t, so then y would be equal to negative 2t squared plus 1. We could also let x be equal to t cubed. That would be another way to do this. So y would be equal to negative 2 times t cubed squared plus 1. And if we simplify that, that would be negative 2t to the 6 plus 1. So there's our second set, and there's our first set of parametric equations. So let's look at something a little bit different. Suppose we want to find a set of parametric equation that's going to define this curve. We'll start with number 35. Well, ideally, we need to start with figuring out what would this curve be in rectangular form. So we know this is the equation of a line. So let's figure out what the slope would be. Slope is y2 minus y1 over x2 minus x1. So our slope is 1. So then we can use point slope formula to find the equation. I'm going to use this point. So y minus y1 equals m times x minus x1. So y is equal to x minus 2. So that would be the equation of the line if it kept going on and on forever and ever, right? But we want just this parametric piece, and we want to make sure that we get the orientation captured as well. So we could let x be equal to t, and then y would be equal to t minus 2. So now we have to think about what are the restrictions on t, because it's not going on and on forever and ever. There's a finite amount of this line there. So we know that x is bounded between 2 and 7. And if we let x be t, then t has to be bounded between 2 and 7 as well. So there's our set of parametric equations with our restriction there. Now, what if we didn't want to do that? What if we wanted something a little bit more exciting? We still know the linear function. You still have to start there by figuring out what would this be in rectangular form. You could say, I'm going to let x be equal to t cubed, just like I did before. Then y would be equal to t cubed minus 2, because all we do is make that substitution in for that. But we still need to restrict the x's because this does not go on and on forever and ever. So once again, we know that x is bounded between 2 and 7. And we said x is going to be equal to t cubed, so let's make that substitution. And then to solve for t, we would take the cube root of both sides. So if we use this parameterization, we would have to restrict t this way, whereas if we use this parameterization, we would restrict t this way. So your parametric equations and what you choose to substitute in for your x will affect how your t is restricted, but the graph will be the same. So it's pretty cool to think about stuff like that. So let's do another one. Let's look at 38. So with 38, we are dealing with this half ellipse. And this half ellipse has a center at 0, 0. And we see that we move along the x1, so there's our minor axis length, and we move along the y4, so there's our major axis length. So we could think about this as x squared over 1 squared plus y squared over 4 squared is equal to 1. There's our equation. So we can think about this as x over 1 squared plus y over 4 squared is equal to 1. So once again, we're going to relate everything with sine squared plus cosine squared is equal to 1. So if we look at this graph, to me, this looks like it would probably go from negative pi over 2 to pi over 2. So let's try it. Okay. Now, a lot of times with figuring this out for something like an ellipse, and this is going counterclockwise, you got to think about what could it be and then try it and see if it works. So here's my t. I'm going to let x be equal to cosine of t. So there's my x. And then y is going to be equal to 4 sine of t. So x equals cosine of t, and y is equal to 4 sine of t. Okay, and the reason that we got these is because we're making this substitution in here. So I viewed this as cosine of t squared plus sine of t squared. I usually put cosine with x and try that first to see if it works for the orientation. And then sine of t is equal to 4 over y. So then, y over 4. So then to solve for y, we just multiply both sides. So there's my y. So let's create this chart. Let's see if the orientation works. If it does, we're good. If it doesn't, then we need to try different values for theta. So if we plug in negative pi over 2, cosine of negative pi over 2 is 0. Sine of negative pi over 2 is a negative 1, so this would give us a negative 4. So we do start here. Plug in 0. We're going to get 1 and 0. So we've got here. And then pi over 2 is at 0.4. So you can see that the orientation is correct and that we're moving along this counterclockwise, starting here and going there.